paradigm of machine learning, that is deep learning, at the end. So let us begin with what is learning. So if I ask you what is learning, many of you would define it in different way. So learning denotes, as a cognitive psychologist Herbert Alexander Simon says, learning denotes changes in the system that are adaptive in the sense that they enable the system to do the tasks drawn from the same population more efficiently than previously, right? So, for example, you must be remembering your old childhood days when 3-4 numerical problems where a concept was explained, like solving a quadratic equation or finding the roots of a cubic polynomial, whatever. And then by illustrating 2-3 examples, your teacher would ask you to solve rest of the problems. And by looking at the problems you were able to solve, system is the same, I mean the entire thing are the same, but you were able to solve more complex problems. Coming to just like household problems, making say paratha or roti, many of you who are good in cooking might be knowing that initially when you wish to make a paratha, the shape, size are not exactly what you wanted, but then with practice you do it. So what is meant? The same population means the same data. With the same data, I have more experience and I can do better. So that is the idea. So that is what is known as learning. Now, machine learning, if I look at machine learning, you have in the previous lecture, you might have heard, and you may be also having experience, that machine learning is a field of computer science. But in this is a branch of AI that gives computers the ability to automatically learn without explicitly being programmed. What is meant by automatically learning? So it is learning from experience on data to make any prediction, right? So we can say it is concerned with the design and development of algorithms that allow computers to evolve behaviors by experiencing the data, okay? So if I look at a very simple example of, say, learning algorithms that we see, we have certain data. That data, this data can be, for example, the data of blood samples, the data of images, X-ray images, or whatever data. So suppose you have a data set and you wish this machine learning algorithm to learn the data so that it can make predictions. What kind of predictions? By looking just at the blood samples or at the X-ray reports, can this machine learning algorithm make prediction that the patient is COVID affected or not? So I have certain samples. Suppose these are, say, we have some 500 samples of data. Now these 500 samples of blood samples have reports. So some 20-30 parameters are there in the blood report. And from those 20-30 parameters, machine learning algorithm is able to extract patterns, and then based on those patterns, it is able to classify whether COVID affected or not, right? So suppose out of these 500 samples, I show it some 450 samples. I show the machine learning algorithm, I give as input these 450 samples, right? And out of those 450 samples, suppose it is able to make, say, predictions up to, say, 60% accuracy. 60% times it gives the correct prediction. Now, who tells that this prediction is correct or not? Because these 500 samples were already shown to the doctor, and doctor had labeled them that these samples belong to the category of COVID affected and not COVID affected. So initially what we do, we give them some labeled data. In this case of learning, I'm giving labeled data. So it is making predictions, and 60% times it is making correct predictions. But I'm not happy with this. What I'll do, I will again, the next time, I will be again giving the same data. So the data is given, predictions are made. I'm not very happy with the predictions made by the machine learning algorithm. So what I'll do, I will again give these 450 data samples. Again, it will be making predictions. We'll try to understand better the patterns present in the samples. And suppose next time it makes, say, some 70% better predictions, 70% accurate predictions with 70% accuracy. I'll keep on giving this data again and again. These are known as epochs, my dear friends, right? So suppose after 10 epochs, 10 times I've shown this 450 samples, and finally it turns out that it is giving me accuracy of, say, 98%. And then I say that, okay, 2% error is okay, acceptable. Then I will be showing the remaining 50 samples which were there already. We only showed 450 samples. So remaining 50 samples I will be showing to the algorithm. Okay, and these samples, on these samples also, if suppose it is making predictions approximately 97 or 98%, then I am true. All right, then I say that, okay, even on some of the unseen examples, it was making corrections properly. So for example, during the class time, the teachers give you some problems, and you keep on solving similar problems or those problems shown by the teacher. But in the test time, the teacher gives you some unseen problems, right? So similarly here, these 50 samples are chosen for validation of the accuracy or validation of the prediction performance of the machine learning algorithm. All right, so suppose this has happened. Now I'm happy that, okay, 98, 97% it is showing on this validation data. This is known as the validation data. Which data? Which we have kept, but we have not shown to the machine learning during the time when it was trying to learn the patterns of the data. That is known as a training time. Now, so my doctor ready, he's happy with the performance of the automatic determination, automatic prediction, and he will deploy in his hospital this automatic system. Next time the new patients will come, and suppose the prediction was 99%, then I will say that my machine learning model has actually learned in the real world problems, in the real world scenario, not problem. Problem is for prediction of COVID affected or not. That is the idea. So remember that we are doing training and we are doing testing. In between, we have a method which we call as a validation method. Those 50 samples we have shown for validation, we have kept for validation, right? So suppose you have this universal set unobserved. There are so many people who may be suffering from cough and cold and fever, but they have never reported to the hospital. Suppose out of these, we have taken some, say, 20,000 samples, and we put them into categories: COVID affected, not COVID affected. This data is kept shown to the machine learning algorithm, and during the training, it learns from experience by observing the data. It learns to extract the patterns, right? So then it makes prediction. Now, once this prediction performance is good, then the unknown samples from the real world problem are shown to the machine learning algorithm. So what is training? Training is the process of making the system able to learn. Okay. Now, so if a machine learning algorithm, I can say is, when we say it has learned. So I say that a machine learning algorithm is able to learn and extract patterns from the data uh, when we say that you have an experience E. Experience E means data. What kind of data? It can be natural language processing data. It can be speech signal data. It can be image data. It can be any numerical data. So experience on the data by observing the data. With respect to some class of tasks, T, what kind of tasks? It can be a classification, whether COVID affected, not COVID affected. Uh, Language, whether in this language you have to do the summarization of the text, that is the task. Or it can be an image classification, or it can be an object detection within an image. All these tasks are called tasks. So with respect to some class of tasks, so I say that a computer program, that is our algorithm, is set to learn from experience E with respect to a class of tasks T and performance measure P. If what happens, if its performance on the tasks given to it as measured by P improves with experience E. So I told you that first time it made 60% accuracy, then it made predictions with 70%, and then finally, after 10 times showing the same data again and again, it improved its classification accurate performance. So how the performance is measured in this case? Accuracy. We used accuracy to measure the performance. So it says that a machine learning algorithm, it learns by looking at the data, having experience on the data, and its performance is measured by some performance measuring performance measure. And then we say that, okay, it has improved or it has done well. That is what is known as training. So if I look at the learning algorithms, my dear friends, there are three broad categories of learning. Now, so many other types of learning are also coming out, but you will find in the literature three broad categories of learning. One is known as supervised learning, the method that I told you, that you have labeled data, data with labels. So doctor was able to get time to label all those 500 records, right? That is what is supervised learning. So data with label is shown to it gives its output, and then the number of what the feedback is given based on the errors it has made. Now, the second method is known as unsupervised learning. What is that? Suppose the hospital is flooded with COVID patients. Now you hardly have doctor, right? So what do? That you keep, getting the total number of those blood samples record. And then there is a technician who is not a doctor, but he, based on his past experience, maybe he will be trying to figure out which one might be COVID affected, which one or not. So he will be sampling them and putting them in two classes, right? Without actually knowing whether they are samples of COVID affected persons or not. So there's no label, but the technician does it, right? Finally, he puts it in output classes, but then doctor measures the performance by looking at whether those clusters, those two classes, which are groups that it has made, are correct or not. So some unsupervised learning. The third is based learning. So reinforcement learning is based on the current environment. Suppose there is an artificial agent it can be your computer program, algorithm. We understand that that means the state of the current environment is known. Based on the current state, if an action is taken, I may be rewarded or I may be penalized. Based on this, it takes some actions, right? Experiencing, based on the past experience, it may be having no past experience as well, because if it starts initially. So what happens, that based on the um, actions, it gets some rewards and it gets some penalty as well. For example, if you try to learn the bicycle, initially you fall down, right? But then you find out the best strategy so that you can maintain the balance between those pedals and you keep running the bicycle. So that is very much possible. That is what we can say is a reinforcement learning. Some people are saying that my audio is breaking sometimes. Close the chat panel because the weak connectivity. I don't know, chat panel, it doesn't, I don't think chat
Ma'am,
panel does have.
I think if you close your video, probably we can have a better audio.
So you are getting my voice breaking?
Yes,
Voice is
ma'am.
breaking?
It is breaking sometime. Yes, ma'am.
Okay. Okay, fine.
Yeah, probably
Now
it might
please
help.
tell me whenever the voice is breaking.
Okay, ma'am.
Yeah, thank you. So so that is the idea, right? But then there is another kind of learning which is known as semi-supervised learning. So semi-supervised learning is when the doctor was able to identify out of those 500 samples some 25-30 samples. So very small data, a small number of data samples are labeled, rest of them are unlabeled. So how to devise algorithms making use of this small number of labeled data and large number of unlabeled data. That kind of learning algorithm is known as semi-supervised learning. And then finally comes the imitation. I mean, there are so many other kind of learning, as I told, but imitation learning is another kind of learning where by looking at the some experts' behavior or experts' action, I will be also taking proper action. I will be taking actions and I will be understanding the patterns and will make prediction. So, for example, by watching your friend, how does he ride a bicycle, you also learn how to ride a bicycle. So that is what precisely is, I mean, we can say is imitation learning. So let us look, I mean, let us try to understand what exactly is supervised learning. So you have sufficient number of examples of a random vector X. What is the random vector in case of blood samples? So blood sample is a random vector, and you take any patient who comes to a hospital is a randomly coming patient who is giving his blood sample. An associated label Y. Y is whether COVID affected or not. This label can be itself a vector, right? So, for example, the output has to be generated like COVID, malaria, um, typhoid, and XYZ kind of thing, other viral fever. So then in that case, Y will become a vector. So COVID affected, yes. Malaria, no. Typhoid, yes. Other viral fever, no. So it can be like that. And learning supervised learning deals with observing some sufficient number of examples and an associated label Y and learning to predict Y from X. Now, estimating the probability, basically we are estimating the probability uh, of occurrence of Y under the condition that X has occurred. Like given an input X, you would like to find predict the label Y under the condition that X is given to you. So example, given an image data set of satellite images, each image is tagged as, for example, forest, desert, water body, or city, right? So X, given X, image X, its label is one of these labels, right? So after having enough examples from satellite images, the program learns the feature of each type of image. And on a new image not seen earlier, it will give the probability of P given X, given input image X, whether it is containing a forest or so. Supervised learning, you can see that it will have training samples, which could be a text, document, image, sound, whatever. And then some feature vectors are extracted from the training sample. Generally, we extract best possible features so that the machine learning algorithm learns better. Like a teacher tells, there are a certain way to understand the pattern of factorizing a cubic polynomial, right? The teacher may tell you that, okay, look at this 6, which is a coefficient of x square. Is it having some relation with the coefficient of x cube and x? And then try to break this up into 2 parts. This is how teachers tell you. So they tell you the patterns to learn to solve a numerical or mathematical problem. Now, along with that, along with each data sample, some labels are given, as I told you. Then the algorithm makes prediction. And then once this learning is over, new text documents are produced, which are features are extracted, and then they are sent to the predictive model, and the expected label is what is the outcome of this. Unsupervised learning, on the other hand, uh, will be is based on observing again the sufficient number of examples of a random vector X, like the blood samples, and attempting to implicitly or explicitly learn the probability distribution. So suppose the samples are coming from a data distribution, from some, the samples are coming from, say, distribution, and this distribution is of, say, different age group. So under 10, 10 to 20, 20 to 30, and so on and so forth. And you see that the patients who are coming are mostly from, say, from this sample, like this age group. And so some of the samples, so actually the age group in a population is, suppose in Indian population is like this, and you have taken samples from the different age groups, and then you see that, okay, these patterns are coming, these age groups, patients with these age groups are coming. So there's hardly any, I mean, there are not many data data samples, but you would like to learn the distribution, the actual distribution from where the data is coming. Okay, this is the probability density function. So sometimes this probability distribution function that is there, this function of the age group, function of different age group, this is approximated explicitly. That means we model the px value sometimes, or sometimes it is implicitly modeled. That is, we are only interested in the new samples. We are not interested in basically modeling this probability. Right? So since there is no label attached with the random samples, the algorithms must learn to make sense of the data without any guide. Example, from a cluster of cells in a given image samples, to identify features that classify cancerous and genuine cell, right? And now, so unsupervised learning, you see that there's no label here. The rest of the things are exactly the same, okay? Now comes the reinforcement learning. Now reinforcement learning as a is a different kind of machine learning paradigm, where what happens, it deals with agents that must sense the state of the environment, world, they call it world, and take appropriate action to fulfill the objective. Objective can be, optimizing certain thing, or finding out the best path in a robotic path planning environment. So the current action influences the state of the world, which determines its reward. So what happens is that, for example, environment. Think of a robot moving or exploring in a jungle, right? Now, the idea is to reach to a water body. Now, by looking at the current state of the environment, current state of the world, what you will think that, okay, most of the people have walked, there is appears to be a lane which is going towards some deep forest. So you will probably will be going on those lanes which are made by different footprints of different people, right? So most likely you are moving towards a water body, or you are moving towards some other part of the jungle. So what happens that based on the current state, the agent takes some action, and then either a reward is given to the agent, or a penalty like minus times reward. So initial state is S0, I take an action A0, I get a reward R, I go to the next state, I take an action, I get again a reward, and this sequence continues until I reach the goal. That is how reinforcement learning works. So learn from interaction with the environment to achieve the goal. Let us take this simple example. Here, suppose the start position is this and the goal position is suppose this. So reward at each step is 0 minus 0.04, right? So it's basically a penalty. So what is the strategy to achieve the maximum reward? Remember that here, reaching here, I get a reward +1. And reaching here, I get a reward of -1. So actions could be up, down, left, right. So in computer games, you must have seen such examples where if an entity, artificial agent, or an agent which you are trying to control is making some actions and either rewarded or penalized. Normally what happens that transitions and rewards are usually not available, but you have some goal. So how to change the policy based on the experience? You have made a policy that I will go straight, but when you go straight, you will have some kind of odd experience. So how to change the policy based on experience, and how to explore the environment there in this case of reinforcement learning. Reinforcement learning based, what kind of training is provided? Well, initial background knowledge may also help, because you know that if I have the experience of the tennis court, so I can probably do better against my opposite player. So the extent to which it was made available to the algorithm, that is background knowledge. The type of feedback provided, whether there was any feedback provided or no feedback was provided. What was the data set size and quality? Quality of data sometimes can also be bad, like from a very noisy audio, you are expected to recognize the voice of 2-3 people. So it can be a very difficult task. But if the data set is very clean or kind of balanced, then it is easy for people to perform well. So the learning algorithms use what learning algorithm have you used? Is it a support vector machine or neural network or naive-based classifier in case of classification? Well, there are two important factors that you must remember. One is modeling. How do you model your problem? Okay. And then so suppose you have modeled the problem, that means you have understood what is the main objective. What is the objective that you want to achieve? Then once the objective is defined, how do you optimize your policy, your actions, so that you get an optimum result? So these are two important factors. I hope my voice is not breaking.
Ma'am, it was paused for a fraction of second, but much better now.
Okay, because I'm using a Wi-Fi. Somehow my this
No issue, ma'am.
this optical fiber connection somehow is not working.
It's okay, ma'am, because
Yeah.
some words are
Okay.
if some words are breaking, we get it continuously, so it's not an issue. Not an issue.
I'm extremely sorry for the experience, but this is
Ma'am,
the
it's
best I
very
have
rare.
right
I
now
mean,
presently.
it's very rare, ma'am. It's very rare. Just once happened. Once you
Okay.
close the video, no, after that, it happened once only for a fraction of second. So it's not an issue, not at all.
Okay. Yeah. I wanted to keep, I mean, I keep my video on because at least I should be seen to the people. It is such
Yeah, but
a different experience. You know, you are teaching, you are delivering lecture, and you don't know to whom you are doing it.
that's the
Anyway,
irony, ma'am.
so some people are saying the audio is right now. Thank you
Yeah,
so
ma'am.
much for
It's
your.
right now.
Thank you so much. Yeah. So main objective, like in case of supervised learning, to minimize the average of error. Like what is the average error of finding correct y for each sample x, right? More precisely, you actually minimize, suppose there are m samples, so you will be minimizing the distance between actual sample, actual label y and the predicted label y hat, okay? So suppose it is a Euclidean distance, then y minus y hat norm. That is what you will be doing. Excuse me. So y is the predicted value of the actual ground truth value of each sample x. Let us take this supervised learning simple example that you have a binary classification problem. So labels are given. These are samples. For each sample, I have a label, right? And the label that is predicted is 0.99, 0.32, 0.80. So what I will do, I will take mean absolute error as my error measuring norm. So I take y minus y hat. I take the difference between them, find out the absolute value, and will take, because there are 4 samples, so I will take the average error. So generally, a supervised learning objective is to find out the minimum, this minimum of this mean absolute error. So idea is to minimize this by giving experience of the data again and again, okay? Now in unsupervised learning, however, we don't have samples, we don't have, labels. So suppose the data sample is a blood test reports of 1,000 patients. Based on certain features of blood samples to identify patients in which category, like COVID affected, malaria, typhoid, viral fever, none of the category. But the diagnostic may be wrong. The basic idea is to minimize the diagnostic error here in this case. So there are certain measures of for finding out later. Once everything is done, then certain measures are applied to check whether this is correct or not. The kind of diagnostic that has been done is correct or not. Now, before we go ahead, let me tell you something about some very common terms that we use in machine learning. One is called generalization. What is meant by generalization? the ability to perform well on previously unobserved inputs. So I told you those 500 samples, if they were shown to the machine learning algorithm, and then the algorithm is deployed as a automatic system as the at the front end of a hospital, and the new blood sample comes, if the algorithm works well, then that is what is known as generalization. Training error, the error observed in the training set. So if the error keeps on going down, you will keep on giving this experience of the data again and again. At certain point, you know what happens? The error next time, first experience of the data, error is this much. Second, the error is this much. Third, the error is this much. Fourth, and finally, what will happen? The error will be almost like having not much change. So then you can stop training, right? Because then probably either you are happy with the error, not very large error, or you would like to check what is wrong with the machine learning algorithm, that the error is not going a certain level. So that is known as training error. Now, test error or generalization error, expected value of the error on a new input. So suppose it is making, it is making, suppose it is having an accuracy of 98%. So in the new sample out of 100, you would like some 2-3 samples to be misclassified. Rest of the samples, it should classify well. That is known as the test error. Underfitting is what? When the model is not able to obtain sufficiently low error value on training set. And overfitting is what? When it overlearns from the number of samples which are given. I give you a simple example. Like the pattern, you know, in case of COVID, initially what happened, the patients came who were mostly from the 40 plus category. So the age group is there. So the pattern of the disease, like how does it change your body system, was coming from here only, from higher age group. This is higher age group. So this pattern was not understood for children below the age of 10, below the age of 12, right? Now this year it is spread over the entire population. Most of the population was affected, young people, middle-aged people, and old age people, everybody was affected. So what I mean to say, initially, if suppose the data sample that you get are not from the entire population, distributed from the entire population, then it may happen that it overlearns the patterns of this population only, this type here only. It will not be able to perform well on a new population. So when the gap between the training error and the test error is large, that is known as overfitting. And what is regularization? Regularization is basically any modification that you make in your system to reduce the generalization error. That is known as the regularization. Not the training error, remember. It is the test error. That is on unseen example how the system performs. You will be making any changes either in the objective function or on the model or on the whatever you want to see accordingly. You will make regularization. Let us take this simple example of overfitting where the data was coming from a sine curve. Data was coming from sine pi to pi x. And because of some error in the channel, noise in the channel, this epsilon was added. So you can see that the samples are taken like this. Samples are either exactly on the sine curve, or they are a little away from the sine curve. Then suppose you are applying a polynomial regression. So the very high degree polynomial I take. So it is passing through all the data points, a polynomial of degree 9. But then what happens? You can see if I want to approximate it at this point, it will give me a very large error. If I want to approximate it at this point, it will give a very large error. Similarly here, it will give very large error because that is what is known as overfitting, right? So how to prevent overfitting? First of all, large data set can help overcome overfitting. Dropping certain hypotheses like model capacity, very high degree polynomial. You could choose a lower degree polynomial. That can also help. Classical regularization methods were like to constrain the hypothesis, like the model capacity, that was one. Adding some regularization factor in the main objective function, right? Something you have to optimize in machine learning, okay? And then other methods included data augmentation, early stopping, all these methods are there. So learning algorithms, unsupervised learning algorithms, you must have had the experience of using these algorithms or must have read these algorithms like principal component analysis, generative models of neural networks like autoencoders, clustering, k-means, hierarchical, graph-based clustering, all these are examples. Matrix factorization, these are examples of unsupervised learning algorithms, right? Then support vector machine, linear regression, decision tree, artificial neural networks, these are used in supervised learning, right? So these are some of the very famous algorithm you might have used in your research problems. And excuse me. So let us take one of them, like artificial neural networks. So what is an artificial neural network? An artificial neural network. So I can see some questions. Can you please elaborate generative models? Samtha is asking. I'll come to that, Samtha. Please wait for a while. So let us look at the artificial neural network. What is artificial neural network? Many of you might be knowing that it is an information processing paradigm which is inspired by human brain's information processing mechanism. Like our neurons are the single independent units of information processing. They work like a computer, right? So like it's parallelly everything is being processed by each neuron, and then they work in unison, right? So composed of a large number of highly interconnected processing elements that you call neuron working in unison to solve specific problem. Now, ANN learn by examples like human learn. Humans learn by examples. Similarly, ANN or neural networks also learn. So if you look at the neurons in the brain, you see that this is a nucleus. There are certain components like synapse, dendrites, axon. The main purpose of neuron is to receive signal, analyze signal, and transmit further the information in the form of signals. So when a neuron sends information, we say that it fires. Okay? Acting through specialized projections known as dendroids, as you can see here, and axons, neurons carry information throughout the neural network. And synapse here, they work like memory of the neuron. Okay. So let us take a mathematical model. This is one of the best possible models that we are using right now. Although research is on building better and better models for neuron. So how neuron works? Let us take an input. Suppose the input is a say color input. Color input, you have, you know that it has 3 channels, red, green and blue. So the neuron has to learn the color from the input. The components which are given, red, green and blue, it has to make prediction about the color. So what will happen, that each neuron will be giving a different weight. It will associate a different weight to the input parameters or input signal. So that is, it can happen like, for example, it is giving say x1 w1 weight. So it will be x1 w1 plus x2 w2 plus x3 w3. This is all assembled here, summing up the input. And then after this, on this input, I apply a function, right? So I will be applying a function here, f on this input. That is known as a activation function. After the function is applied, the output of this function goes as an output to the action, you know that it can be any kind of action that is required. Take x1, x2, x3 as these, then these are say corresponding weights, and then I have summed up those weights. Say z is equal to the sum of weighted sum of this. Suppose that turns out to be 4.1648. Excuse me for a while. Sorry. So let us take an activation function. This activation function, which I have taken here, is called a sigmoid activation function. It is defined as sigma z is equal to 1 upon 1 plus e to the power minus z. And its value, you can see, lies between 0 and 1. So it never touches 1, but it is approximating in like this. This is an asymptote, and this is also an asymptote. Y is equal to 0 and y is equal to 1 are two asymptotes, right? So it is very close to 1. So 4.1648 is then given as to the sigmoid function, and the whatever is the output, that is this output, will come out from the neuron. That is how it does. Now, so how the training is done, let us see. Here if we have this vector which has got 3 components which we call as features. Features of this vector, the corresponding class is given. Suppose it is a binary classification problem, and we have 3 neurons which are processing the information. This is known as the input layer, right? This is known the input layer. This is known as the hidden layer. Why hidden? Because this is only working to process the information, but it does not output anything to the rest of the world. But this is known as the output layer because this is what gives you the action command, or whatever you want to say it, call it. So you have 3 neurons, and each of these neurons will be receiving this data one by one. So I train the neural network by initializing the randomly the weights. For each neuron, 3 weights will be initialized. Why? Because there are 3 inputs. So 3 weights for each neuron. So 3 cross 3, that is 9 weights, will be initialized. But then each neuron has a bias parameter also. Just like you and I have bias towards, like we have our own likings and dislikings, neurons are also modeled to have biases. So each neuron will have a bias parameter B1, B2, and B3. So 9 parameters plus 3 bias. So 9 weight plus 3 bias. And then the last output neuron will also have 3, because it will receive 3 inputs. So it will also have a 3 weight. So 3 cross 1, plus it will have its own bias. So plus 1 bias. So how many total weight parameters? There are 9 plus 3, that is 12 weight parameters, plus 4 bias parameters. So this neural network is having 16 weight and bias parameters that will be randomly initialized. Okay. Then I present a training pattern and feed it to. Training pattern means this I'm presenting and feeding it to the neural network. I will get an output and compare it with the actual value, right? And then the expected output is 0, whereas I'm getting 0.8. So the error is 0.8. Okay, I will adjust and update the weight because it is making a lot of error. So I will be adjusting the weight and updating the weight. Then we'll keep on producing, giving training patterns one after the other. So next time I am giving this sample and the output is 0.9, error is minus 0.1, 0, minus 0.1. So error is decreasing in some sense. So in this way, I repeat the process to reduce the error. Okay, that is how neural networks are trained. Time, and each time a random training example is taken, weights are slightly adjusted, right? Well, you must be thinking that how this is happening. Basically, it may not be an efficient adjustment initially, but eventually the process of weight adjustment leads to a good enough model for producing an effective classifier in this case. And it works well in many real life applications. So if I look at the multi-layer perceptron, why does it help? Why does it produce good results? Because universal approximation theorem says that any continuous function over a compact domain can be accurately approximated using a neural network. So what is a function here? Input is x, the label is y. So fx is equal to y is the function that we are approximating, right? This is the function that we are approximating. So this function can be accurately approximated using a neural network with one hidden layer only. But it also says if the layers increase, the accuracy of approximation increases. So there is a mathematical theory behind it, and that is why multi-layer perceptron work well. So to deal with non-linearity and for better approximation, you know that multi-layers are introduced, and activation function are also helping in getting the non-linear characteristics of the data. So this is the input sample and the output layer. Fine. These in-between layers are known as the multi-layer. They are known as the hidden layer. So my dear friends, back propagation happens like this. Like I will be inputting the vector, hidden layers will be processing it, output will be given, compare the output with the correct answer to get the error signal, and then back propagate the error signal to get the derivatives for learning. Why derivatives? Because you know that you want to minimize something. So the gradient points to the maximum direction, like maximum rate of change. I will be going in the opposite of the gradient direction. And that is why I want to find out the gradient of the error. So this is suppose I want to reach the minimum. So I will be going in the opposite direction to the gradient. That is why error derivatives of the error are computed. So in neural networks, we choose a learning rate alpha, and we update the weights like this. W is equal to W minus del J by del W, where what is J? J is the average error. For in case of say 50 samples, this is average error. So error is definitely a function of W. So for any particular parameter, W is equal to W minus alpha del J by del W, and similarly for bias parameter. So this learning rate is very important. A very large learning rate like 0.1 may give you high oscillation, and you may not converge to the real, close to a minimum value. And so sometimes taking a very small error value, learning rate helps. So you have to take care of this. So how the training is provided? Training is provided like sample label data, for example, forward it through the network, get the predictions, back propagate the error, update the network weights. So optimize the cost function, or what is the cost function here? It is the average error, which depends on all W's and all B's, all weights and all this. And I use the error signal to change the weight and get more accurate prediction. Okay. So it leads to a local minima of the cost function. Remember, this is not an optimization problem. Here we are improving the prediction performance of a machine learning algorithm. And if the user is satisfied, say with 99% accuracy, or with an error margin of say 0.05, minus 0.05 plus 0.05, then we will be stopping our training there. Okay, that is how it happens. Oh, sorry. I'm extremely sorry. This is the last slide. I jumped to the slide. So I would like to take questions and give you a small break before we go ahead with the next part of this.
Actually, there is a question. Kiran Bhaumik is asking, why do we need bias and how it helps in learning?
Just a minute. I wish to see the. I wish to see. So how does it help in learning, right? Just a minute. Can you please explain the need of bias and how does it help in learning? Well, so bias, that is a kind of degree of freedom given to every neural network. See, in the same layer, neural networks are working in unison to give you an output. So suppose there is in the same layer, there are 5 neurons or 5 units. We call them units in computer science. So there are 5 information processing units, neurons, right? Now, all of them, suppose these 5 have to learn whether the input color is say a combination of green and blue is say yellow color or not, right? So yellow color, like some people will be rigidly following like 50% of green and 50% of blue, then I will be calling it yellow, right? So what happens that these are given extra freedom to think and learn that, okay, if the range of green and blue varies between, say, 0.5% here and there, then also I will call it yellow color, right? And so the other neuron will say, okay, I will be giving a variation of, say, 7% here and there to call it a yellow color if it is not 50% green and 50% blue, but it is some, say, some 54% green and say some 66%, sorry, 46% blue. I will still call it a yellow, right? So yellow color, you know that it has several shades of yellow. But then how those several shades can be learned together? So the idea is that this extra degree of freedom to learn is given to neurons, right? How does it help in learn? I think I have already uh, explained. How does it help in learning? Because it learns to understand the variations. It learns to get to it learns to have variations also. But if I look at the number of weights and number of biases in a neural network, my dear friend, it is number of weights are too many as compared to number of biases. So affecting a model effect on a model's performance is dominated by weights than the number of bias parameters. So some authors, some researchers even neglect the bias parameters. But my suggestion is that you can think of, you can make an experiment, you can experiment with small neural networks, large neural networks, and see how does bias parameter help. Thank you. Any other question?
There's another question which is, how do we know if data set is accurately labeled or not?
Uh, how to check if data set is accurately labeled or not? Well, this only human intelligence can tell from experts, field experts only, they only can tell. For example, one of my students is working in biomedical image analysis. So, although he can label because he knows, but then until and unless a doctor certifies, validates it, I don't think he can. We can call this that the data set is correctly labeled. So suppose a computer science students understanding the patterns of the disease labels a data set, doesn't mean that the data set is correctly labeled. Only a human expert can, correctly predict it, correctly tell.
Actually,
So
ma'am, this
there
is a
can be
problem we are also
non-accurate.
facing. This is ground truthing. So ground truth creation is a very big challenge because it has to be done manually and by the domain expert only. So we were working on a problem of image
Yes.
processing in which we had to identify individual farm boundary. So in that, the ground truth that we had was very
Uh-huh.
wrongly labeled, wrongly marked. The farm boundaries, there were a lot of footpath which were marked as farm boundary, and a lot of different wrong markings were done. So ground truth was not accurate.
Huh.
That is why our algorithm failed repeatedly to perform. And once we actually set ourselves and identified the farm boundaries, then the same algorithm gave much better result. So it is definitely a
Yes,
human.
very
Yeah,
right. Yeah.
yeah.
So human error as are possible, and as you are rightly telling that it may happen that these are wrongly labeled, then your data set becomes can have like such kind of noise because of wrong labels.
It's exactly like
So that does
a human
affect the
child.
model's
If
performance.
we, it's like human
Yeah.
child. If we teach the right things, the child will learn the right thing. We teach the wrong thing, the child will learn
Yes.
wrong. So
Learn the wrong thing. I agree with you completely. Very good example, Dr. So reading, Feeding the data reduces the error, but when the sample volume changes. Madam, re-feeding the data reduces the error, but when the sample volume changes. Well, are you asking the question or you are making a suggestion? I don't understand. So
Chetan, if you want
sample
to speak
volume,
up,
like
you
if
can
suppose
unmute yourself and say something if you want to ask question. Okay, there is another question. Can we trust online data repositories? Of course, you can trust.
yeah. So deciding the bias weight is like how we decide the other weight, right? Yes, yes. Biases are also randomly chosen, but generally in the bias parameter, you will find that they're chosen zero. You will find many GitHub codes where these are chosen zero. Um, do we have any process of weight and bias initialization? Yes, there are standard methods of weight and bias initializations. These are randomly chosen, right? So those random process initialization processes are also, there are some very well-known methods which are existing in the literature. This validation, like you are, suppose you're building a self-driving car. So when you are building a self-driving car, initially you will test in the lab its performance in the lab itself. Then after the lab performance is over, you will definitely take it to your campus. Within the campus, you will run the car self-driving. Once that campus, within the campus, it runs well, then you will put it on the road. So training within the lab, validation within the campus, and testing outside the campus. White screen is coming because I am not sharing my slides. That's all. Now I come back to my slides. So what kind of neural networks? There are various types of. Why take always an activation function? Uh, Madam, why always take an activation of bias is one? No, we never take bias as one. We take bias as an independent parameter, and the activation function is applied on the total sum. So it's not nothing like bias is one. Yes, we can use SVM have proven to be very good regression problem solver. Regression. Yeah. So there is another question. Input of bias, madam. Input of bias. Input of bias. That bias is itself input as a random variable, right? So there are various types of neural networks that we have seen. Convolutional neural networks are there, recurrent neural networks are there. Then you have variants of these basic types of this neural networks have been introduced by researchers for different tasks like, say, language modeling, object detection, salient object detection, segmentation, all these things are done. Of the traditional machine learning algorithms, like they usually use manually designed features. These manual, like I told you, example of a blood sample. Whenever you go to a doctor, he will ask you to go for blood test, and there can be some 20-25 parameters. But if you look at those parameters, you will not gain anything. The doctor, on the other hand, will look at some 5 significantly important parameters for a particular disease. He will first look at, for example, at your ESR count, whether there is infection or not. And then the doctor will also check for hemoglobin count, how much it has affected your hemoglobin, and those things, right? And then it will look at other correlated terms. So first it will look at the some say significant parameters. So although the pathologist will give you some 20 parameters output, the doctor's interest is on some 6 parameters or 7 parameters. These are what is known as manually designed parameters. But in case of machine learning problems, we really don't have any idea as to what patterns are to be understood, are going to help machine learning algorithm learn to make predictions. So we often over specify them. There are sometimes incompleteness in the features that we take. They are mostly application dependent also. Like these cannot be generalized easily to other applications. Like I told you, for if you have to detect malaria, those different types of input features will be important. If you have to detect, say, typhoid, then different parameters will be important. So these are application dependent, cannot be generalized easily, and they're time consuming in design and validation. Like one of my students was working on software maintainability, and then it took long time to understand that which input parameters, which design parameters are important features for predicting the software maintainability, right? So developing handcrafted features is a costly and complex job. Let us take the simple example of, say, image captioning, where the simple caption is a bird hiding in a bunch of flowers. So what happens? Initially, I will be giving the color the color feature of this bird, a flower, then bird's beak, feather, and all those things. Those features will be extracted in terms of edges, colors, and other, say, some histogram thing. And then they will be sent to a trainable, that is your machine learning algorithm, and then it will make an output. There is another problem with the traditional machine learning algorithm that is known as curse of dimensionality or peaking phenomenon, which says that suppose you have 200 samples of images. Now, this image, initially, we used to have in MNIST data set or any other data set, you have a 32 cross 32, like you have 32 cross 32 images, right? Or you have 64 cross 64 images. Now, think of your mobile. It has images which are, say, 40 megapixel, 30 megapixels. So, suppose you have a 32 cross 32 image and you want to make prediction. So it will, performance will be somewhere here, suppose, in terms, suppose some measure of performance. Then it is 64 cross 64. It will improve. Then I make it, say 128 cross. It will further improve. But now if I take it, say 512 cross 512, it will drastically reduce. So with only 200 samples, suppose I have to detect an object within an image, and if I keep improving the resolution of the image, the curse of dimensionality theorem says that with a fixed number of training samples, the predictive power of a classifier or regressor first increases as the number of dimensions is increased, but then decreases. And so many machine learning algorithms problems become exceedingly difficult when the number of dimensions in the when the number of dimensions increase, right? For example, what kind of problems? Say, so here is the pattern that I'm showing, prediction accuracy. So what kind of problems are important? Like, the speech recognition, voice modeling, or language modeling, or object detection within an image. All these are very important problems. So what could be the solution? Deep learning has emerged as a powerful solution to many problems that could not be handled efficiently by conventional ML algorithms, right? So these algorithms where deep learning has done very well are, say, natural language processing, machine translation, language modeling, medical diagnostics based on, say, image understanding, signal analysis, gene expression analysis, traffic prediction in wireless network, anomaly detection, defense mechanism, all these things are places where deep learning has done very well. So what is the difference between the machine learning and deep learning? What happens that when we take, say, suppose that you have an image data set where the image is of some scene where you have to identify that this scene contains a car or not, right? Initially, manually features of this image will be extracted. Then they will be fed to a classifier algorithm. And then the output will be found out. So this is how training is done. This is the training, and even the prediction is made by this. But in deep learning algorithms, the feature extraction work and the classification, they are done by a single algorithm or the single at a single stage. So you can see that the entire work of fetching the features or extracting the features which are right for a particular problem is now automated. This feature extraction and classification is done it becomes a part of automatic extraction. That is one of the biggest difference between the traditional machine learning algorithms and deep learning algorithms. So traditional neural network classifiers were requiring features to be extracted. But if I look at the deep neural networks that is shown here, like it's a depth 4 neural network. So this is a very shallow network, in fact. But deep neural networks, they do take the abstraction as well. Artificial intelligence, it started with a heuristic search and then evolved with a knowledge bases. And then came the idea of machine learning with logistic regression, those classifiers like SVM and all those. Then came the idea of representation learning, my dear friends. Representation, trying to understand the data representation, how data can be best represented. So deep learning is a representation learning paradigm where the basic structure or the backbone of the deep learning is a neural network, right? So it is a neural network that is used. Okay, so if I look at the AI ML DL, you see the AI deals with algorithms that mimic the intelligence of human, is able to resolve problems in the way we consider smart, from the simplest to most complex of the algorithms. Whereas if I look at in this block, the definition given of machine learning, algorithms that parse data, learn from it, and then apply what they have learned to make informed decisions. They use the human extracted features from data and improve the learning experience. Whereas in deep learning, if you see, neural network algorithms that learn the important features in data by themselves. So it is automatic learning of features, able to adapt themselves through repetitive learning or training to uncover hidden patterns in the data insights. Okay. So deep neural networks have many hidden layers, and some of them have even more than 100 layers, like residual network, ResNet 152, which was the first neural network introduced by Kang-Min He in 2015, which outperformed the human intelligence in terms of computer vision. First neural network which could do well in understanding from the image number of different classes of objects, that is classification of objects, as well as detecting, that is which object class instance of a class is belonging to which place of the image, right? Identifying and locating different object categories in an image. An average human is making some say 5% errors, was making 5% errors in 1.4 million images of 1000 object categories, but it made an error, say around some 3.57 or so, if I remember correctly. So the large number of layers have large memory footprint. They need high computation resources. Large number of layers also lead to vanishing and exploding gradient problems, which say maybe some people in the future lectures will tell you what is this. Basically, when the gradients vanish, then algorithms don't learn anything. So new training algorithms have evolved. New deep neural network architectures have been proposed over the years that have led to their significant performance improvement in practically every field, including, not communication, including, say, images, communication, right, and natural language processing, and many areas. So if you look at the developments in AI with deep learning, if you look at the internet and cloud, image classification, speech recognition, language translation, in medicine and biology, like drug discovery, media and entertainment, like video captioning, real-time translation, security and defense, and autonomous vehicles. All of you have already seen all these examples, right? My dear friends, you must be thinking that I'm only speaking about neural networks, but that is what is dominating these days. I would like to ask us to answer some questions like, if the image is resized, is there any effect in error? Okay. So yes, if the image is resized and if the information is like resizing is a lossy compression, then definitely it will be having effect on the performance. What is the purpose of word embedding? Now, word embedding, like, you have, say, in your dictionary, suppose you have 20,000 words. So it's a very high dimensional data that you will be dealing with. So word embedding helps you reduce the dimension of the input samples, and that's why we use word embedding. So there are various word embedding methods that help us reduce the dimension of the input samples. So AI, like the AI is a, like, it's a, you can say, is a big package where we are looking at, say, in what way human intelligence is helping solve real life problems, right? So machine learning is what machine learning does. Does the same thing by looking at, by experiencing the data samples and learning to extract useful patterns from the data, right? So in machine learning, what happens? That the data that is given to the machine learning algorithm is not only pre-processed, but some features are extracted from the data to help machine learning algorithm learn better. In deep learning algorithm, data is definitely pre-processed, like word embedding is a kind of pre-processing that we do. Data is pre-processed, images are resized, and word embedding is done in case of natural language processing. So data is pre-processed, but then features, one doesn't bother to extract features. And that feature extraction part is automatically done in a very nice way. Why? Because deep learning is a kind of representation learning. It learns to represent the data, right? That is what is done. So, how to decide a best train and test proportion? So Pavandeep, what happens when you have say only 1,000, some 5,000 data, less than say 5,000, 6,000 data, that is not compared to the population. Like suppose that total population is 10,000, but you have 5,000 data, so it is a large data, right? If your total population is say lakhs, millions, and you have taken only say some 5,000 data samples, then in that case, generally people say who are from machine learning, who are machine learning experts, they say there's a 70-30 proportion, 80-20 proportion, both can work well. But if your data set is pretty large, say suppose it is 50,000, 60,000, 1 million, 1 lakh. So in that case, you can take some say 95% training and 5% testing, or 98% training if it is very large. You can even take 98% training and 2% testing. So it depends on the size of the data set. Now I come to deep unsupervised learning. So deep unsupervised learning, for example, autoencoders and generative adversarial networks are most frequently used in deep unsupervised learning. These are generative models. Many of the autoencoders are generative models. Like variational autoencoder is an example of a generative model, right? Autoencoders are used for representation learning, feature selection, noise removal, and approximating the data distribution, right? And then GANs, that is generative adversarial networks, they provide an excellent way of generating artificial or synthetic data that has properties very similar to real data. For example, face images. It can produce very nice face images that look absolutely like humans, but they are not real humans. They are fake humans, right? So let us go to autoencoders for the time being. What is an autoencoder, my dear friend? As the name suggests, autoencoder must be encoding something, right? So an autoencoder is a neural network that is trained to reproduce its input, right? What is this? Idea is that the autoencoder learns a representation that is called encoding for a data set, typically for dimensionality reduction. But now autoencoders are also used for many different purposes. So when the neural network is trained to learn data representation, it ignores noise present in the data samples. So along with dimensionality reduction, the neural network also learns to generate the data from its encoded vector Z. That is the reason we call it an autoencoder. So let us see what is the idea. So suppose you have samples, right? So you have samples, like this is input sample, sorry. Yeah, this is what is happening? This is an input sample. Here is a neural network, right? This neural network will produce some output. That output, I call it a latent representation or code for X. Now this is sent to another neural network. This is another neural network, and that neural network sends an output. Now I expect this input X and output X hat to be similar. So X hat is basically X's reconstruction. I'm reconstructing X by making use of Z, which is its encoded part. So X is encoded to Z and Z is decoded to X hat. So the idea is, how can I reduce this error, the difference between these two how it is minimized. So autoencoder is this network, this set of two networks, neural networks, which is trained to minimize the error between the reconstructed output and the actual input. So giving data X, no labels, we would like to learn the function F, that is encoder, and G, that is decoder. Learning the function means what? Learning the weight parameters of this neural network so that Fx is equal to Z and GZ, capital Z, is equal to X hat, and this X minus X hat is minimized, right? So basically it is learning the identity representation. It is learning this h-axis g of fx is an approximation of the identity function because I'm reconstructing. That is the idea. So activation function in the hidden layer helps extract nonlinear features of the data characteristics. So this is your active, this is x plus bias goes to z, and then z plus bias goes to produce x hat, which is a function h depending on the weights and the bias parameters. So this h wbx should be the same as x. This is what we want. And if you see in the MNIST autoencoder results, very simple autoencoder if you use, very simple neural network, then this will be very effectively producing. This is the original data set, images, original images, and these are reconstructed images. No labels are given, remember. So that is, you can say, is an unsupervised learning. So in summary, I would say machine learning is a branch of AI in which algorithms are developed that automatically learn the data patterns to take decisions. And there are several types of learning like supervised, unsupervised, and semi-supervised also, reinforcement learning. And imitation learning is emerging as a good alternative to reinforcement learning. Support vector machines and neural networks are examples of supervised learning algorithms, and neural networks are also used in unsupervised learning. I gave you an example. Machine learning has led to several developments in practically all fields that touch human life. And what is the real game changer, my dear friends? It is the deep learning. That is the real game changer. And so challenges with deep learning are there right now. It is working like a black box. Why it has taken a decision? There is no interpretation, right? No explanation of the predictions made by deep learning models. So new directions of research are explainable AI or interpretable machine learning. And these are some of the new emerging directions of machine learning. Well, before I conclude, I would like to tell you the institute where I belong to. It's at Indian Institute of Information Technology. Dr. Munindra Ojha has already told you about that. We have a residential campus of 2,000 plus students with 3 engineering streams, and we have design and natural sciences as well. And so it's a beautiful lush green campus of 250 acres, and it's a growing campus. So these are some of the references you would like to see. And that is my last slide. Stay safe and healthy, my dear friends.
Ma'am, would you
Thanks
be
for
able
your
to
patient
share a
listening.
slide?
Pardon?
Would you be able to share these slides
I'm
because a lot of
sharing my
participants
slide.
I mean, email these slides. So
Okay. Fine. I will definitely share this. Sure. I will share. I will share the slides. So any questions if you have?
in fact, there are a lot of questions. Some Pawandeep is asking them how to decide best test and train proportion. Is it 70-30 or 80-20?
So that I answered him that if you have relatively small data set, then 70-30 is okay. If you have better data set, like suppose you have only 300 samples, in medical imaging, we have somewhere 300, 500, 2000 samples, then use 70-30. If you have 5,000, 10,000 samples, then you can use 80-20. If you have 50,000, 60,000, you can use say 95, 98% for training testing, right? That I have told. And then I'm sorry, Manish, it is not helping me like unshare this whiteboard. I don't know what's happening.
It's okay, ma'am. I
Uh,
think we have already reached the end of the
yeah,
session, so it's okay.
yeah.
So
Any
I
other questions?
can we use DL for numerical data set?
Yes, definitely.
Hmm.
Numerical data set, give me any example of data set. I will tell you which numerical DL you can use, right?
Ma'am,
Thank
in
you
fact,
so much
we
for
are
your
all
nice
the
compliment.
images are even converted to numerical values. So ultimately, what we feed are
Yeah,
numerical values itself,
yeah.
right? So, hmm,
The numerical data, like if you see time series data, if you have any speech, I don't know what kind of numerical data you're talking, stock market prediction, everywhere deep learning is used.
yeah. Thank you, ma'am. It's a very nice session. It was very lengthy and it was tough. Actually, they have made it 2 hour, but it has become very tough to get 2 hour long session. Normally, we should have a break. But it was very
Yeah.
kind of you and very nice that you explained all these concepts very beautifully. And it's the ideal start of this workshop that we were actually hoping for. With your presence, we have got that, ma'am. Thank you so much, ma'am. Thank you.
Thank thank you. Yes. So I am really thankful to you, Dr. Muneen. It is always a pleasure giving lectures in these workshops, and especially if you are organizing it, I will definitely be
My pleasure.
there to help you, support you, and I'm so happy to see you at Allahabad. And
Yeah,
let us hope that this trend continues and we keep on organizing these programs which are useful for people.
sure, ma'am.
Thank you
Sure.
all the participants also. It was
Yeah,
such a nice interactive session. I liked it.
yeah.
So I take your leave, Dr. Muni.
Okay, ma'am. Okay. Thank you, ma'am.
Thank you so much, all the participants. Thank you.
Bye.